Find a power series representation for the function below centered at x equals 0, then determine the interval of convergence. We have f of x equals x divided by the sum of 3x squared and 1. To determine the power series, we'll use the known geometric power series below, which is 1 divided by the quantity 1 minus x equals the sum from n equals 0 to infinity of x to the power of n. Notice this is centered at x equals 0. To use this, though, we'll have to have a difference in the denominator and a numerator of 1. Let's write the given function as x times 1 divided by the quantity 1 minus negative 3x squared. And now we can write a power series for 1 divided by the quantity 1 minus negative 3x squared by replacing x in the geometric power series with negative 3x squared. But we still have a factor of x outside the power series, which gives us x times the sum from n equals 0 to infinity of the nth power of negative 3x squared. And now let's write the nth power of negative 3x squared as negative 1 to the power of n times 3 to the power of n times x to the power of 2n. Now we multiply x and x to the power of 2n. When multiplying and the base of the same, we add the exponents, which gives us x to the power of 2n plus 1. We now have a power series representation for the given function, which is the sum from n equals 0 to infinity of negative 1 to the power of n times 3 to the power of n times x to the power of 2n plus 1. To determine the interval of convergence, we will apply the ratio test, and therefore we'll determine the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, which must be less than 1 for the series to converge. A sub n is the given formula. To determine a sub n plus 1, we replace n with n plus 1. Notice the exponent on x is now going to be 2n plus 3. And now let's set up the limit. We have the limit as n approaches infinity of a sub n plus 1 divided by a sub n. Because we're taking the absolute values, the negative 1s really don't matter. But notice negative 1 to the power of n plus 1 divided by negative 1 to the power of n simplifies to one factor of negative 1. When dividing and the bases are the same, we subtract the exponents. 3 to the power of n plus 1 divided by 3 to the power of n simplifies to one factor of 3. And x to the power of 2n plus 3 divided by x to the power of 2n plus 1 simplifies to two factors of x, or x squared. We now have the limit as n approaches infinity of the absolute value of negative 3x squared. And now determining the limit is equal to 3x squared. Notice x squared is always positive, which to converge must be less than 1. To solve for x squared, we divide both sides by 3. Solving the quadratic inequality, we have x is less than 1 divided by square root 3, and x is greater than negative 1 divided by square root 3. If we were asked to determine the radius of convergence, the radius of convergence is 1 divided by square root 3. We also now know the series converges on the open interval from negative 1 divided by square root 3 to positive 1 divided by square root 3. However, now we have to see if the series converges or diverges at the endpoints. Let's work on this on the next slide. Let's first consider x equals positive 1 divided by square root 3. To do this, we substitute positive 1 divided by square root 3 for x in the power series. For the next step, let's write the square root of 3 as 3 to the power of 1/2. And now let's apply the exponent of 2n plus 1 to the numerator and denominator of the fraction. Well, 1 to the power of 2n plus 1 will always be 1. And then for the denominator, we multiply the exponent of 1/2 by 2n plus 1, which gives us positive 1 divided by 3 raised to the power of n plus 1/2. Again, notice 1/2 times the quantity 2n plus 1 is n plus 1/2. And now we can simplify 3 to the power of n divided by 3 to the power of n plus 1/2. This simplifies to 3 to the power of 1/2 in the denominator. Analyzing the power series, it looks like it will diverge. Let's apply the nth term divergence test, which remember states if the limit as n approaches infinity of a sub n doesn't equal 0, then the series diverges. So now let's take the limit as n approaches infinity of negative 1 to the power of n times 1 divided by 3 to the power of 1/2. Notice as n approaches infinity, the values oscillate from positive 1 divided by 3 to the 1/2 to negative 1 divided by 3 to the 1/2 because of the negative 1 to the nth power, and therefore the limit doesn't exist. And now we know the series diverges at x equals 1 divided by square root of 3. And now we'll test x equals negative 1 divided by square root of 3. First step, perform substitution for x. Let's write negative 1 divided by square root of 3 as negative 1 in the numerator divided by 3 to the power of 1/2 in the denominator. And now again, we'll apply the exponent of 2n plus 1 to the numerator and denominator. Applying the exponent to the numerator, we have negative 1 to the power of 2n plus 1. In the denominator, again, we multiply the exponents, we have 3 to the power of n plus 1/2. Negative 1 to the power of n times negative 1 to the power of 2n plus 1 is negative 1 to the power of 3n plus 1. And again, simplifying 3 to the nth power divided by 3 to the power of n plus 1/2 simplifies to 3 to the power of 1/2 in the denominator. And again, this will fail the nth term divergence test. We take the limit as n approaches infinity of a sub n. Once again, the values oscillate between positive 1 divided by 3 to the power of 1/2 and negative 1 divided by 3 to the power of 1/2, and therefore the limit doesn't exist, and the series fails the nth term divergence test. We know it diverges at x equals negative 1 divided by square root of 3. The series diverges at both endpoints, and therefore the interval of convergence is the open interval from negative 1 divided by square root of 3 to positive 1 divided by square root of 3. I hope you found this helpful.